Semiconductor device performance is critical for many products that affect our daily lives. Faulty products result in customer returns and dissatisfaction and ultimately lost revenue to the product manufacturer. So how do manufacturers verify the performance of semiconductor integrated circuit devices to ensure end product operation? And how do they test those IC devices cost-effectively? As prices drop on network and consumer electronic products such as wireless hubs, DVD players, HDTV, graphics, digital cameras, and cell phones, the electronic devices inside must meet aggressive manufacturing cost targets in order for companies to remain competitive and profitable. But often the quality assurance test can be costly, especially when precision measurements are required to guarantee device performance. This is why GuideTech focuses on extremely high-throughput precision test solutions that replace traditionally slow-timing test methods such as digital edge search, oscilloscope, and spectrum analyzers to enable characterization measurement accuracies at production speeds. Higher test coverage means better quality assurance and fewer customer returns. Faster test times mean lower test cost and higher profit margins. When timing is critical to break IC test cost barriers, GuideTech has solutions to enhance and extend the life of any existing ATE. Since 1988, GuideTech has specialized in precision timing instruments based on innovations in CTIA, continuous time-stamping timing interval analyzer technology, with over 1,500 systems installed worldwide at commercial and scientific organizations such as NASA, the CERN European Nuclear Research Center, the NIST National Institute of Standards and Technology, and the U.S. Naval Observatory, where GuideTech products help keep the world's master clocks synchronized. Today, GuideTech develops products for the semiconductor test industry that break the IC test barriers of precision timing analysis and speed of test in high-volume manufacturing. GuideTech CTIA instruments integrate onto any semiconductor ATE system, enabling precision timing measurements with test times that are affordable on even the most cost-sensitive consumer ICs. Customers trust GuideTech to lower their costs, particularly for testing of challenging signals, such as the emerging high-speed serial interface technologies like PCI Express and serial ATA, signals which are problematic for traditional synchronous ATE due to the unpredictable output timing of these clock-embedded serial interface signals. And GuideTech's proven superior performance and cost savings have made GuideTech the de facto standard at all major fabless subcon test facilities worldwide, and test programs that were developed on the GuideTech Femto 2000 are compatible with the GT4000 for easy migration to higher performance phase noise and serial interface jitter analysis. GuideTech is uniquely positioned to break cost barriers in the semiconductor test market with its CTIA time-stamping technology, which eliminates the need for pattern markers or clock data recovery measurement alignment and makes it ideal for testing any type of asynchronous or non-deterministic signal such as the emerging PCI Express and other high-speed serial interfaces. And while PCI Express and other high-speed serial interfaces were designed to improve performance of data transfer within PCs, cell phones, and networks, an IC manufacturer can guarantee the devices will operate correctly in real-world systems only if the quality of these high-speed signals has been adequately screened for signal integrity issues in final manufacturing test. Simple functional loopback testing has been a traditional method of screening good devices from bad, and in many cases parameters like signal jitter were only guaranteed by design and never tested in production. GuideTech CTIA products uniquely address the challenges of asynchronous phase-lock loop clocks used in cell phones, TV tuners, and graphics video devices by enabling test of PLL clock and spread spectrum frequency, jitter, lock time, bandwidth, and phase noise at test speeds viable for high-throughput manufacturing. So while GuideTech has been filling the ATE gap with solutions to address the test challenges of asynchronous and non-deterministic PLLs and serial interfaces, there are many simple timing test applications which can also be optimized to dramatically reduce test time using features such as parallel test and block mode arming to iterate measurements that need to be repeated several times. Take the example of TV tuner devices. where the tuner's frequency oscillator must be measured and trimmed repeatedly during test until the oscillator's frequency is trimmed precisely to within the tuner's tolerance margins. With test time so fast, customers require fewer test systems and can even continue using older test systems by just enhancing them with a few channels of GuideTech's high-performance timing measurement capability. When timing is critical to break IC test cost barriers, customers come to GuideTech to enhance their new or extend the life of their existing ATE. At GuideTech, we provide solutions that enable reliable, high-throughput, precision measurement capability on any ATE and at every major test company. GuideTech products are based on powerful continuous time interval analyzer time-stamping technology. Without requiring the assistance of arming triggers or pattern markers, CTIA instruments trigger timing measurements directly on the signal edge being measured and record a timestamp for each measured edge containing the event count or pulse number and a time value of the measured pulse edge relative to a common reference clock in a system. Real-time DSPs compute timing measurements from the timestamps in milliseconds. Multiple types of timing measurements can be computed from the same set of timestamps, further improving test throughput. All CTIA measurement channels measure independently and asynchronously to provide the maximum flexibility for testing non-deterministic signals, such as phase lock loops and high-speed serial interfaces with unpredictable output phases. Another major advantage of CTIA technology is that all measured timestamps on every channel in a system are correlated to the same reference clock time, enabling precise skew measurements across all CTIA measurement channels. Unlike traditional digitizers or samplers that measure changes in voltage over time, where time values of interest must be extracted from large data sets and post-processed, the CTIA system directly measures changes in time over time. By measuring only the edge timing of interest, CTIA timing analysis is performed with extremely high throughput with the advantage of being capable of performing single-shot measurements, such as PLL lock time, as well as long-term trend analysis of timing behavior in a signal, such as clock jitter and spread spectrum modulation. In addition to spread spectrum modulation and PLL lock time, basic CTIA timing measurements include frequency, period, pulse width, phase noise, skew across multiple channels, rise and fall time, and time interval error that is typically used to determine low-frequency clock jitter and wander. And since a CTIA executes measurements in only milliseconds and on multiple channels in parallel, customers achieve precision timing measurements on any semiconductor test system with multi-channel and multi-site throughput that is viable for use in high-volume manufacturing test. Traditional methods of determining the quality of a data signal include statistically analyzing jitter PDF histograms and verifying a signal's eye diagram using an oscilloscope or counting the number of bit errors to determine transmitter bit error rate using a BERT or bit error rate tester. However, analysis of scope-generated edge jitter histograms requires the capture of thousands of data points to minimize PDF curve fit estimation errors. Plus, BERT instruments must test millions of streaming data bits to guarantee very low bit error rate. Thus, both scope and BERT methods tend to be slow, often taking minutes or hours, and therefore are generally not cost-effective for high-volume production test. Loopback test has often been employed to provide an inexpensive way to loosely determine if a device is good or bad. But as emerging multi-gigabit serial interfaces reach higher and higher data rates, accurate jitter analysis of the transmitter output signal integrity is becoming increasingly more important. This is due to the fact that determining the magnitude of each component of random and deterministic jitter enables prediction of device performance in real system applications, performance that may be difficult to guarantee when a device passes only simple tests like loopback test in a clean test environment. To break the cost barrier of testing these emerging high-speed serial interfaces in high-volume manufacturing test, GuideTech has developed revolutionary jitter measurement techniques using CTI technology. These techniques enable fast analysis and separation of measured jitter into its various random, periodic, and data-dependent components. Analysis has proven that by accurately determining random jitter in a transmitted data signal, the transmitter bit error rate can be estimated to a high degree of accuracy. One of the key advantages of CTI technology is its ability to make accurate random jitter measurements in milliseconds instead of minutes or hours. However, since the BER estimation equation multiplies random jitter by a large Q factor for any given BER, the larger the error in random jitter measurement, the more likely the bit error rate estimation will falsely determine a normally good device as bad. This erroneous failure of normally good devices can dramatically increase test costs if the random jitter measurement is imprecise. Since precision is the key for random jitter measurements, it is important to verify that the random jitter test method guarantees immunity from influences by other elements, such as data-dependent jitter and periodic jitter in the signal. Test methods that lump all measurements into a single statistical curve-fit analysis, where DDJ and PJ components are not easily separated from the Gaussian random jitter histogram, are prone to significant curve-fit estimation errors. GuideTech timestamping CTIA with its direct measure of each jitter component is not. The repeatability of random jitter measurements under various circumstances is evidence that an instrument is accurately separating jitter components in a signal. This demonstration of the GuideTech CTIA illustrates how random jitter results remain stable while applying two different patterns and while sweeping the data rate. First, random jitter is injected onto a data signal using the noise generator. As the test pattern is altered between K28.5 and PRBS7, and as the pattern bit rate is swept from 1 gigabit per second to 2.5 gigabits per second, the CTIA random jitter results remain stable, unaffected by variations in data rate or pattern type. One of the negative consequences of measuring random jitter using the statistical curve-fit analysis methods of scopes and older TIA technologies is the error that is introduced by curve-fit estimations when a jitter PDF histogram is contaminated by data-dependent jitter. The ability of a CTIA to directly measure and record timestamps of each measured signal edge is the secret to CTIA jitter separation accuracy. The continuous time correlation between measured timestamps, all correlated to a T0 of a common system reference clock, acts as a virtual pattern marker and enables the CTIA to isolate jitter PDFs of a measured data signal on a per-edge basis to easily extract DDJ edge shift errors before computing random jitter on the measured timestamp values. To demonstrate that the GuideTech CTIA random jitter results remain stable while applying varying amounts of data-dependent jitter onto the test signal, a noise generator is set to inject a known amount of RJ, and an arbitrary waveform generator is used to vary the amount of DDJ injected onto the test signal being measured by the CTIA. Any high-frequency or low-frequency jitter in a data signal can cause errors in a jitter PDF curve-fit estimation of random jitter. Such jitter reveals a significant limitation of most scopes and older TIAs. A CTIA eliminates curve-fit estimation errors by being able to directly measure the periodic jitter present in a data signal before computing random jitter. To demonstrate the CTIA's ability to remove periodic jitter from the measurement data before computing random jitter, first, the noise generator is set to inject RJ onto the test signal. Notice that when high-frequency periodic jitter is injected by modulating the high-frequency signal generator, the CTIA random jitter results remain stable. Notice that when low-frequency periodic jitter is injected by modulating the low-frequency signal generator, the CTIA random jitter results remain stable. CTIA continuous timestamps record trends in edge timing shifts over time. Because all CTIA timestamps are referenced to the same master clock, the data can be processed to determine trends in time errors over time. Time-correlated timestamps make it easy to perform FFTs to determine periodic jitter frequencies and to compute edge timing errors versus ideal edge locations to extract data-dependent jitter from a data pattern on a per-edge basis. Scopes and traditional TIAs require pattern triggers to synchronize timing measurements with selected signal edges. One of the advantages of CTIA technology is its ability to measure timing without the need for triggers, pattern markers, or clock data recovery. The CTIA's continuous timestamping of direct edge measurements enables direct and reliable measure of edge timing on asynchronous and non-deterministic signals of unknown output phase. The advantage of markerless CTIA measurements is that every measured edge time value is associated with a bit event count. This allows the CTIA to always keep track of where that measured edge should have been located, given a known pattern and known unit interval bit size. When measuring a repeating data pattern, CTIA timestamps can reconstruct a data pattern to perform functional pattern verification on any non-deterministic signal, effectively providing a virtual marker without the pattern depth and jitter tolerance limitations of hardware pattern markers and arming triggers. Large amounts of jitter can be injected onto the test signal, and the CTIA is still able to measure the signal reliably. When we move the same signal over to a scope, it does not take long to find where the scope loses lock on the signal when too much jitter is injected for the scope trigger to handle. As clocks and phase lock loops push to higher frequencies, phase noise becomes an important test parameter to assure device quality in final manufacturing test. The time-correlated nature of CTIA, continuous timestamping technology, facilitates fast Fourier transfer, or FFT analysis, of jitter frequencies and amplitudes in a measured signal. The ability to analyze phase noise on a CTIA is like having a fast spectrum analyzer built into the same CTIA instrument, thus making the CTIA one of the most flexible and cost-effective solutions for precision timing tests on any ATE.